All right, so let's get started. Today we're going to talk about what are probably the two most famous theorems in the entire history of probability. They're called the law of large numbers and the central limit theorem. They're closely related, so it makes sense to do them together, kind of compare and contrast them. I can't think of a more famous probability theorem than these two. So the setup for today is that we have IID random variables. Let's just call them x1, x2, IID. And let's say they all have, since they're IID, they have the same mean and the same variance, if the mean and variance exist. But we'll assume they do. So the mean, we'll just call it mu, and the variance, sigma squared. So we're assuming that these are finite for now, that the mean and variance exist. And both of these theorems tell us what happens to the sample mean as n gets large. So the sample mean is just defined as xn bar. Standard notation in statistics, we put a bar to mean averages, and that's just the average of the first n. So to take the first n random variables and average them. So that's just called the sample mean. Okay. So the question is, what can we say about xn bar as n gets large? So we're the way we would interpret this or use this is that we get to observe these x's, they're random variables, but after we observe them, they become data. And if we have, we're never going to have an infinite amount of data. So at some point, we stop at n. We can think of that as the sample size. And hopefully, we get a large sample size. Of course, it depends on the problem. Some problems you may not be able to get large n. But we assume n is large and just take the average. The question is just, what can we say? All right, so first here's what the law of large numbers says. It's a very simple statement, and hopefully pretty intuitive, too. Law of large numbers says that xn bar converges to mu as n goes to infinity with probability 1. That's the fine print, probability 1. With probability 0, so something really crazy could happen, but we don't worry too much about it because it has probability 0. With probability 1, this is the sample mean, and it says that the sample mean converges to the true mean. Okay, so that is a pretty nice, intuitive, easy to remember result, right? That is this by true I mean the theoretical mean, that is the expected value of xj for any j is mu. That is the true expected value, whereas this is a random variable, right? We're taking an average of random variables. That's a random variable. So this is just a constant, but this is a random variable, but it's going to converge. And I should say a little bit more about what does this convergence statement actually mean. I mean, you've all seen limits of sequences, but when we're talking about limits of random variables, we have to be a little more careful about how do we actually define this. The definition of this statement is just pointwise, which means, remember, xn bar is a random variable. Random variable, mathematically speaking, is a function. So it says for each possible, if you evaluate this at some specific outcome of the experiment, then you get a sequence of numbers. That is, you've actually observed the values, and this kind of crystallizes it, into numbers when you evaluate it at the outcome of the experiment. And so those numbers converge to mu. In other words, this is an event. Okay, either these random variables converge or they don't, and we say that event has probability 1. That's what the statement of the theorem is. Okay, so to just give a simple example, let's think about what happens if we have Bernoulli p. So if xj is Bernoulli p, then intuitively we're just imagining an infinite sequence of coin tosses, right? Where the probability of heads is p, okay? And then this says that if we add up all of these Bernoullis up to n, that is just in the first coin flips, how many times did the coin land heads, divided by the number of flips, should converge to p with probability 1. So for example, so this is a very intuitive statement, right? Like if it's a fair coin and you flip the coin 1,000,000 times, well, you're not really expecting that it's going to be exactly 500,000 heads and 500,000 tails, right? But you do think that in the long run, you know, it should be the case that it's going to be essentially half heads, half tails. Not exactly, but essentially. And the proportion should get closer and closer to the true value. This qualification with probability 1 is needed because mathematically speaking, even if you have a fair coin, there's nothing in the math that says it's impossible that the coin would land heads, 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 heads forever. You know that that's never actually going to happen in reality, right? It's just not going to happen, right? It's a fair coin. It's okay. It might land heads, heads, heads for a long time if you're very lucky or unlucky or whatever, but it's not going to be heads, heads, heads forever, right? But there's nothing in the math that says that's an invalid sequence. Okay? So you know, there's some like weird pathological cases like that, but with probability 1, we get what we'd expect. If we didn't have this result, how would we even ever estimate p, right? Like you know, you might imagine if you didn't know what p was, kind of the obvious thing to do is flip the coin a lot of times and take the proportion of heads and use that as your approximation for p. But what justification could you have for doing that approximation if you didn't have this? Okay, so this is a very, very necessary result. But I guess to comment a little bit more about, you know, what does it actually say for the coin, because this is kind of related to like gambler's fallacy and things like that. The gambler's fallacy is the idea that, like, let's say you're gambling and you lose like 10 times in a row, and then it's the feeling that you're due to win, right? You know, you lost all these times, and you might try to justify that using the law of large numbers and say, well, you know, the coin landed, let's say heads you win money, tails you lose money. You just lost money 10 times in a row, but the law of large numbers says in the long run it's going to go back to 1/2 if it's fair. So somehow you need to start winning a lot to compensate, right? That's not the way it works. Okay, the coin is memoryless. The coin does not care how many failures or how many losses you had before. So the way it works is not through, like, if you were unlucky at the beginning, that somehow it gets offset later by an increase in heads. The way it works is through what we might call swamping. That is, like, let's say, you know, the coin landed tails 100 times in a row. It doesn't mean that the probability has changed for the 101st flip. What it means, though, is that we're letting n go to infinity here. Okay? So no matter how unlucky you were in the first 100 or the first 1,000,000 trials, that's nothing compared to infinity, right? So those first 1,000,000 just get swamped out by the entire infinite future. So that's the, you know, what's going on here. Yeah. So to tell you one little story about the law of large numbers, a colleague of mine told me this story, that he had a student once who said he hated statistics. And of course my colleague was very shocked, like, how can anyone hate statistics? And so he asked, why? How is it possible that you hate statistics? And then the student, who was an athlete, and he was training every day, and he had just learned the law of large numbers, and he was very, very depressed by this, because he said the law of large numbers says in the long run I'm going to only be average, and I can't improve. So, well, of course, the fallacy there, we assumed IID right now, you know. And now there are generalizations of this theorem beyond IID, but we can't just get rid of IID. So IID is saying that the distribution is not changing with time. That doesn't mean that you can't actually improve your own distribution, then it would not be IID. So, okay. So don't be depressed by this. And in fact, In fact, this theorem, I think, is crucial in order for science to actually be possible. Because if you kind of imagine kind of hypothetical, counterfactual world where this theorem was actually false, that would be really depressing to try to ever learn about the world, right? Because this is saying you're collecting more and more data, you're letting your sample size go to infinity, and this says you converge to the truth. Right? And then it would be like some weird setting where you get more and more data, and yet you're not able to converge to the truth, right? So that would be really bad. So this is a very intuitive, very important. Okay, so let's prove this. At least a similar version. So this is actually sometimes called the strong law of large numbers. And we're actually going to prove what's sometimes called the weak law of large numbers. I don't really like the terminology strong and weak here, but that's kind of a standard. Strong law of large numbers is what I just said, where it's converging pointwise with probability 1. And it's just these random variables converge to this constant, except on some bad event that has probability 0. The weak law of large numbers says that for any c greater than 0, the probability that xn bar minus the mean is greater than c goes to 0. So it's a very similar looking statement. It's not exactly equivalent. It's possible to show, if you have to go through some real analysis for this that is not necessary for our purposes, but it turns out that this statement, once you've proven this thing, it implies this form of convergence. This is called convergence in probability. But the intuition is very similar. So it's just to interpret this statement in words, it says, so we can choose, we should interpret c as being some small number. So let's say we choose c to be 0.001, okay? And then it says that this thing goes to 0. So in other words, this is as n goes to infinity again. So this says that if n is large enough, then it's extremely unlikely that these are more than 0.001 apart. In other words, if n is large, it's extremely likely that this is extremely close to this, right? So it's a very similar statement. If n is large, it's extremely likely that the sample mean is very close to the true mean. Okay, so that's what it says. So we'll prove this one, because to prove this one takes a lot of work and a lot of time. This one, it looks like it's a nice looking theorem, and it is a nice theorem, but we can prove it very easily using Chebyshev's inequality. Okay, so let's prove the weak law of large numbers. So all we need to do is show that this goes to 0, right? That's what the statement is. So let's just bound it using, this looks pretty similar to what we were doing last time. We did Markov's inequality, Chebyshev's inequality. This looks similar to that kind of stuff from last time. Which is why I did that. Well, one reason for doing that last time. We need the inequalities anyway, but it's especially useful here. So we just need to show this thing goes to 0, xn bar minus mu greater than c goes to 0. By Chebyshev's inequality, this is less than or equal to the variance of xn bar divided by c squared. That's just exactly Chebyshev from last time. Now we just need the variance of xn bar. Variance of xn bar, well, just stare at the definition of xn bar for a second. There's a 1 over n in front. That comes out as 1 over n squared. And then, since I'm assuming they're IID and independent, the variance of the sum is just n times the variance of one term. So that's n sigma squared divided by c squared, which is sigma squared over nc squared. Sigma is a constant, c is a constant, n goes to infinity, so this goes to 0. So that proves the weak law of large numbers, just only a one-line thing. Okay, so that tells us what happens point-wise when we average a bunch of IID random variables and it converges to the mean. So let me just rewrite that statement, and then we'll write the central limit theorem and kind of compare them. So another way to write what we just showed is that xn bar minus mu goes to 0 as n goes to infinity, which is a good thing to know. However, it doesn't tell us what the distribution of xn bar looks like. So this is true, you know, with probability 1. But what is the distribution? What does the distribution of xn bar look like? So this says it's getting closer, xn bar is getting closer and closer to this constant, mu. Okay, but that's not really telling us the shape, and it's not really telling us the rate. That is, this goes to 0, but at what rate? So one way to think about problems like that, when you have something going to 0 and you want to study something about how fast does it go to 0, then one way to, not just in here, but just as a general approach to that kind of problem, we know this goes to 0, but we don't know how fast. One way to study that would be multiply by something that goes to infinity, right? Now, if we multiply by something that goes to infinity such that this times this goes to infinity, then we know that this part that blows up is dominating over this part. And if we multiply by something that goes to infinity, but this whole thing still goes to 0, then that's more informative, right? So what's going to happen is that we can imagine multiplying here by n to some power. And we're going to show that there's a power here. N to some power, fill in the blank. What we're going to show is that if the power here is above some threshold, then you know, n to a big power is going to go to infinity fast. This thing will just blow up. And if we put a smaller power than the threshold here, then this is still going to infinity. As long as this is a positive power of n, this is still going to infinity. This part's going to 0, but this part's dominating, right? So this term is competing with this term. This one goes to infinity. This one goes to 0. Okay. So then the question is, what's that magic threshold value? And the answer is 1/2. So that's what we're going to study right now. So we're going to take the square root of n times xn bar minus mu. This is kind of the happy medium where we're going to get a non-degenerate distribution. That this is going to converge in distribution to an actual distribution. It's not going to just get killed to 0 or blow up to infinity. It's actually going to give us a nice distribution. Okay? And I'm also going to divide by the sigma here. Makes it a little bit cleaner. So this is the central limit theorem now. I'm stating it, then we'll prove it. Central limit theorem says if you take this and look at what happens as n goes to infinity, converges to standard normal in distribution. By convergence in distribution, what we mean is that the distribution of this converges to the standard normal distribution. In other words, you could take the CDF. I mean, these may be discrete or continuous, or a mixture of discrete and continuous, so it doesn't necessarily have a PDF. But every random variable has a CDF, so it says if you take the CDF of this, it's going to converge to capital Phi, the standard normal. So I think this is kind of an amazing result that this holds in such generality, right? Because I mean, the normal is just this one, standard normal is just this one particular, it's a nice looking bell curve, but that's just one distribution. And those x's, they could be discrete, they could be continuous, they could be extremely nasty looking distributions, right? It could look like anything. The only thing we assumed was that there was a finite variance. Other than that, they could have an incredibly complicated, messy distribution, but it's always going to go to standard normal. So this is one of the reasons why the standard normal distribution is so important on the one hand and so widely used, because this is a theorem, as n goes to infinity is what it says, but the way it's used in practice is then people use normal approximations all the time, and a lot of the justification for normal approximations is coming from this, because this says that if n is large, then the sample mean will approximately have a normal distribution. Even if the original data did not look like they came from a normal distribution, when you average lots and lots of them, it looks normal. Okay, so this is, in a sense, is a better theorem than the law of large numbers, but because it's kind of more informative to know the distribution and know something about the rate. And it's interesting that its square root of n is kind of the power of n that's just right? Larger power, it's going to blow up. Smaller power, it's going to go to 0. N to the 1/2 is the compromise. Then you always get a normal distribution. So it's more informative in some sense, but you should also keep in mind that it is a different sense of convergence. That up here, we're talking about the random variables actually converging. Literally, the random variables converge. The sample mean converges literally to point-wise with probability 1 to the true mean. Here we're talking about convergence in distribution. So we're not talking about convergence of random variables. We're just saying the distribution of this converges to the normal 0-1 distribution. So it's a different sense of convergence. But anyway, both of them are telling us what's going to happen to xn bar when n is large. Okay? Well, let's prove this theorem. Here's another way to write this, by the way. It's good to be familiar with both ways. It's just algebra to go from one to the other, but they're both useful enough to be worth mentioning. Let's just write the central limit theorem in terms of the sum of x's rather than in terms of the sample mean. And so I'm just going to take the sum of xj, j equals 1 to n. And so we can either think of the central limit theorem as either think of it as telling us what happens to the sample mean, or we can think of it as telling us what happens to the sum or the convolution. Okay, it's equivalent because they're just a factor of. We just have to be careful of not to mess up with the factor of n. But we can go from one to the other because it's just a factor of n. So the claim is that this is approximately normal when n is large. But if we just have this thing, this could easily just blow up, right? Like you're just adding up more and more terms. So somehow we want to standardize this first. So if we take this thing, because this thing has mean n mu, right? So let's subtract n mu. Because then it has 0 mean. Because I just want to match I want to make the mean 0 and the variance 1 so that it kind of matches up with that rather than just letting it blow up. So this is called centering. We just subtracted, by linearity, the mean is n mu, so just subtracted n mu. And then let's divide by the standard deviation. This is just how we did standardization before. So over there, we showed that the variance of xn bar is sigma squared over n, and the variance of this sum is just n sigma squared. So it's just divide by the standard deviation, right? Which is square root of n times sigma, okay? Because the variance is n sigma squared. So that's just the standardized version, and the statement is again that this converges to standard normal in distribution. So if we take this sum and standardize it, then it's going to go to standard normal. Okay, so, all right, so now we're ready to prove this theorem. And sort of just a calculation, but it's kind of a nice calculation in some ways. We're going to prove it, well, This theorem is always true as long as the variance exists. We don't need to assume that like the third moment or fourth moment exists. But the proof is much more complicated to do it in that generality. So we're going to assume that the MGF exists. That then we can actually work with MGFs. Because when you see this thing, sum of independent random variables, then we know the MGF is going to be something useful if it exists. And there's ways to extend this proof to cases where the MGF doesn't exist. But for our purposes, we may as well just assume MGF exists. So assuming MGF, let's call it M of t, of xj, they're IID, so if one of them has an MGF, they all have the same MGF. We'll just assume that that exists. Once we have MGFs, then our strategy is to show that the MGFs converge. So that's a theorem about MGFs, that if the MGFs converge to some other MGF, then the random variables converge in distribution, right? We had a homework problem related to that, where you found that the MGFs converged to some MGF, and that implies convergence of the distributions, right? Okay, so that's the whole strategy. So that means all we need to do is find the MGF of this and then take the limit, okay? So it's basically, at this point, it's just like write down the MGF, take a limit, and use a few facts about MGFs, okay? So first of all, we can assume that mu, let's just assume mu equals 0 and sigma equals 1, just to simplify the notation. This is without loss of generality, because we could write this as, all we have to do is consider, I wrote the standardized thing this way, but I could have just written it as standardizing each x separately. I could have written xj minus mu over sigma. So this would be standardizing each of them separately, j equals 1 to n, and then we had a 1 over root n. That would be the same thing that we're looking at. This just says standardize them separately first. But then you could just, if you want, just call this thing yj, and once you have the central limit theorem for yj, then you know that that's true. So you may as well just assume that they've already been standardized. And so just to have some notation, let's just let Sn equal the sum, S for sum, of the first n terms. And what we want to show is that the MGF of Sn over root n, that's what we're looking at, right? Because I let mu equals 0, sigma equals 1. So we're looking at Sn over root n, and we want to show that that goes to the standard normal MGF. Right? So we just need to find this MGF, take a limit. Okay, so let's just find the MGF. So by definition, that's the expected value of e to the t times Sn over root n. And Sn is just the sum. So, and we're assuming independence, which means that these, you can write this as e to the t x1 over root n, e to the t x2 over root n, blah, blah, blah. All of those factors are independent, therefore they're uncorrelated. So we can just split it up as a product, x1 over root n, blah, blah, blah. All same thing, it's just, xj over e to the t xj over root n is the general term, right? Then we're I'm just using the fact that those are uncorrelated, so we can write e of the product as the product of the expectations. But since these x's are IID, this is really just the same thing written n times. So really, this is just this thing to the nth power. And this thing, that should remind you of an MGF. Right? That's just the MGF of x1, except that instead of evaluated at t, it's evaluated at t over root n. So really, that's just the MGF evaluated at t over root n raised to the nth power. So that's what we have. Now we need to take the limit as n goes to infinity, so let's just look at what's going to happen here. N is going to infinity. This thing on the inside becomes m of 0. M of 0 is 1 for any MGF, right? Because e to the 0 is 1. So this is of the form 1 to the infinity, which is an indeterminate form, right? It could evaluate to anything. So going back to, calculus, how do you deal with 1 to the infinity or 0 over 0 or whatever? Usually we try to reduce it to something where we can use L'Hopital's rule for those problems, right? Or we can use a Taylor series type of thing. So how do we get into that form? Take the log. Because this looks like 1 to infinity, if we take the log, it'll look like infinity times log of 1. It will look like infinity times 0. Take logs. Then we just have to remember to exponentiate at the end, to undo the log. OK, so let's write down then what we have. After taking the log, and we're trying to do a limit, so we're doing the limit as n goes to infinity, and we take the log, it's n log m of t over root n. And so that's of the form infinity times 0. If we want 0 over 0 or infinity over infinity, we can just write it as 1 over n in the denominator. Okay, now it's of the form 0 over 0. So we can almost use L'Hopital's rule, but not quite. We have to be a little bit careful because, first of all, I'm assuming n is an integer, and you can't do calculus on integers. Secondly, it's just kind of, even if we pretended that n is a real number, and then the derivative of n would be minus 1 over n squared, and that was kind of annoying to deal with. And it's kind of annoying to deal with this square root here. So let's first make a change of variables. Let's just let y equal 1 over root n, and also let y be real, not necessarily of the form 1 over square root of an integer. Okay, so it's the same limit, just written in terms of y instead of in terms of n. So as n goes to infinity, y goes to 0, and 1 over n is y squared, so the denominator is just y squared. The reason I did it this way is that 1 over root n is just y by definition, but then the numerator is just log m of yt. That's a lot easier to deal with because we got rid of the square roots. So it's still of the form 0 over 0, so we're going to use L'Hopital's rule. So limit y goes to 0, take the derivative of the numerator and the denominator separately. Derivative of the denominator is 2y. Derivative of the numerator, well, we're just going to use the chain rule. Derivative of log something is 1 over that thing. So that's m of yt times the derivative of that thing, which again by the chain rule is m prime of yt times the derivative of yt. We're treating t as constant. We're differentiating with respect to y. So a t comes out. And now let's see what we have. Let's just summarize a couple facts about MGFs. So m of 0, so m of t is the expected value of e to the tx1. So m of 0 equals 1. Okay, and when we first started doing MGFs, we saw that if we take derivatives of the MGF and evaluate it at 0, we get the moments. That's why it's called the moment generating function. So the first derivative at 0 is the mean, but we assumed that mu was 0, so this is 0 here. And the second derivative, while we're doing this, second derivative is the second moment, but since we assumed that the variance is 1 and the mean is 0, the second moment is 1. Okay? So over here, as we let y go to 0, denominator is still going to 0. Numerator is also going to 0, because m prime of 0 is 0. So it's still of the form 0 over 0. So let's just do L'Hopital again. So first I can simplify it a little bit. This t can just come out, because that's acting as a constant, and that 2 can come out, and limit y goes to 0. And this m of yt part, that's just going to 1. So we can write that as part of a separate limit, but that other limit is just going to 1. As I'm thinking of it as the limit of just this part times the limit of the rest of it, but that part's just going to 1, so we can get rid of that. So it really is just what's left is the limit of m prime of yt divided by y. Everything else is gone, so it's actually pretty nicely simplified. Now, using L'Hopital's rule a second time, now the derivative of the denominator is just 1, okay? And then for the numerator, chain rule, m double prime of yt, that was a t, not a t squared, but now it's a t squared because by the chain rule, the derivative of yt is t, so we have a t squared over 2. Now, when we let y go to 0, now it's just m double prime of 0 is 1. So now this limit is just 1. So we get t squared over 2. That's what we wanted. Because t squared over 2 is the log of e to the t squared over 2. But e to the t squared over 2 is exactly the normal 0, 1 MGF. Okay, so to prove that theorem, and that's the end of the proof of the central limit theorem, all we had to do was just, basic facts about MGF, use L'Hopital's rule twice. And then, there we have one of the most famous important theorems in statistics. Now, there are more general versions of this, like you can extend this in various ways where it's not IID, but it still has to satisfy some assumptions, right? But anyway, this is the basic central limit theorem. Okay, so that's pretty good. Let's do an example, like how do we actually use this, for the sake of approximations, things like that. Last time I was talking about the difference between inequalities and approximations, right? And we talked about Poisson approximation before. We haven't talked really about normal approximation. This result is giving us the ability to use normal approximations when we're studying sample mean n is large, okay? So, historically, the first version of the central limit theorem that was ever proven, I think, was for binomials. Okay, so what we're saying is that the binomial NP under some conditions will be approximately normal. And well, in the old days, that was an incredibly important fact because they didn't have computers to, binomial is hard to deal with, right? With n choose k and n is large and k, you have all these factorials. You can't do these things by hand. Now, we have fast computers. It's a little bit better, but it's still a lot easier working with normal distributions than binomial distributions most of the time, right? And even now, factorials still grow so fast that even with a fast computer with a large memory and everything, you may quickly exceed its ability when you're doing some big complicated binomial problem. And normals have a lot of nice properties, as we've seen. Okay, so we just wanted to use, the question is when can we approximate a binomial using a normal, and how do we do that? Okay. So this is just a binomial approximation to the normal, other way around. Normal approximation, I'll say binomial approximated by a normal. It's the normal approximation to the binomial. When is that valid? to contrast it with the Poisson approximation that we've seen before. Okay, so if x is, so let's let x be binomial NP. And as we've done many times before, we can represent x as a sum of IID Bernoullis, right? Or these are just, 1 if success on the jth trial, 0 otherwise. So the xj are IID Bernoulli P. So this does fit into the framework of the central limit theorem. That is, we are adding up IID random variables. So the central limit theorem says that if n is large, this will be approximately normal, at least after we have standardized it. Okay? So suppose we wanted to approximate, suppose we're interested in the probability that x is between A and B. And I want to approximate that. First we'll do equality, then we're approximating that. So, if you had to do this on a computer, what you would do, or by hand, which you wouldn't want to, would be to take the PMF and sum up all the values of the PMF from A to B, right? So okay, you would not want to do that by hand most of the time. But suppose we just want an approximation for this, not the exact thing. So first the strategy is just going to be to take x and standardize it first. So we're going to subtract the mean. So we know that the mean is NP. And we're going to divide by the standard deviation, which we know is the square root of NPQ, where Q is 1 minus P. So I'm just standardizing it right now. So this is still equal. We haven't done any approximations yet. And then, now that we've standardized it, we can apply the central limit theorem if n is large enough. Right? If n is, the central limit theorem said n goes to infinity. That doesn't answer the question of how large does n have to be. And for that, there's various theorems and various rules of thumb. Like a lot of books will say, like, how large does n have to be? And some books, at least, will say 30. And that's just a rule of thumb. That's not always going to work for all. There's separate rules of thumb for the binomial. Like you want n times p to be reasonably large and n times 1 minus p to be large. There are different rules of thumb. But anyway, if n is large enough, then what we've just proven is that this is going to look like it has a normal distribution, because that's a sum of IID things, and we standardized it correctly, because we already knew the mean and the variance, so we just standardized it. Okay, so this is approximately. Now we're going to use the normal approximation. We're going to say this is approximately normal. And if I want the probability that a normal is between something and something, that's just the CDF here minus the CDF here, right? Because for the normal, this is discrete, but we're approximating it using something continuous, and we just say, integrate the PDF from here to here. But fundamental theorem of calculus, that just says take the CDF and go, okay, so we're just going to do phi of b minus np over square root of npq minus phi of a minus np over square root of npq. So that would be the basic normal approximation. I'll talk a little bit about how to improve this approximation. But to contrast it with the Poisson approximation, we talked before about the fact that when we proved the fact that if n goes to infinity and p goes to 0 and n times p is fixed, then the binomial distribution converges to the Poisson distribution. We proved that before. So in the Poisson approximation, what we had was n is large, but p was very small, right? And we let lambda equal np, and I said that's moderate. The most important thing is that p is small here. P is close to 0. we proved it in the case where this goes to infinity and this goes to 0. Okay? So Poisson is relevant when we're dealing with a large number of very rare, unlikely things. That's really in contrast to this. In this case, for the normal approximation, then, well, we still want n to be large, but if we kind of think intuitively about when is this going to work well, we actually want p to be close to 1/2. Because think about the symmetry. If you have a binomial with p equals 1/2, that's a symmetric distribution. The normal is symmetric. No matter every normal distribution is symmetric. If p is far from 1/2, then the binomial is very, very skewed. And in that case, it's kind of doesn't make that much sense to approximate using a normal. So this is going to work as an approximation. That's normal approximation. As an approximation, if p is very small, this makes a lot more sense than this. However, if you think about the statement of the central limit theorem, in that theorem, I never said p was close to 1/2. In fact, that was just a general theorem. We didn't even have p in the statement of the central limit theorem. So somehow this still has to eventually work. But as a practical matter, as an approximation, if p is close to 1/2, this is going to work, quite well. If n is like 30 or 50 or 100, it'll work fine. But if p is 0.001, the central limit theorem is still true, that as n goes to infinity, it's going to work, okay? But if n is just, kind of not that enormous of a number, then, then it's going to be a pretty bad approximation. And let's just try to reconcile these statements, though. Is there a case, if we let n go to infinity and p be very small, I still said if n is going to infinity, it's still going to converge to normal, just much slower, right? So how could it look both? How could the binomial look both normal and Poisson? Well, the answer is that the Poisson also looks normal. So if you have a Poisson lambda where lambda is very large, that's also going to look normal. So there is a case where those come together. Okay, one last thing about this is that there's something kind of weird about this in the sense that we're approximating a discrete distribution using something continuous. And if we wanted to get what if we wanted to just approximate, same problem, I just want to add something to this. Let's just look at just to see more of what could go wrong with this. What if we look at the case a equals b? So then we're just saying, what's the probability that x equals a? That is, approximate the binomial PMF. And one kind of weird thing about this is this thing would change if we changed these to strict inequality, but this part would not, as soon as we say this is approximately normal, then we don't care about that anymore. So there's something called the continuity correction, which I just wanted to briefly mention, which is an improvement to deal with the fact that you're using something continuous to approximate something discrete. And it's often not explained very well, but if you understand what it does in this simple case, then it's not hard to see the idea. The idea is that if you just said, oh, this is approximately normal, then you would just say 0, right? Because it would be 0 for continuous. That's not very useful, right? We want something more useful than 0. So the idea is just simply to write this as, where here let's assume a is an integer. X is discrete. Well, x equals a is the same thing as saying that x is between a plus 1/2 and a minus 1/2, right? So just use this first. So for each value in this range, replace it by an interval of length 1 centered there. That's exactly the same thing because x is an integer anyway, so that's true. But here, at least we're giving it an interval to work with instead of just saying 0. So that improves this approximation. Anyway, it's just central limit theorem. All right, so see you next time.